next speaker, Mr. Saurabh Satish, is an expert on security. He works for the Chief Technology Officer's office, and then he is also a distinguished engineer with 13 years experience in security, network intrusion. He's going to talk more about it. I'm just going to highlight the thing, network intrusion, behavioral model, etc. And he also serves on the advisory board of what's called Voice over IP Security Alliance. And he has been pioneering his work in Symantec in security-related topics. And without much ado, please enlighten us.
All right. Good morning, everybody. So I'm here to talk about big money from big data. It's not going to be the traditional Hadoop talk that if you're expecting. So it's more application-oriented talk. These are my opinions and my only, okay? So who am I? I'm Saurabh. I come from this part of the world, and I live here. This is my family. This is called identity security by obscurity because you really can't see us. This is more personal information than you care. Professionally, if you haven't yet recognized, I work for Symantec. That is exactly where my office is. I'm an engineer, I'm a researcher, innovator, chief architect, and a distinguished engineer by title. I've worked there for 12 years, and that's what it has done to me. I work in CTO's office in the Security Technology and Response Group, where we build engines for the products, which are the core technology that ship in the world-class products that we ship. To basically protect your digital life, we are everywhere, trying to protect users in all kinds of scenarios through a multitude of products. But more importantly, I think you'll recognize us via these products that we ship or you use, many of them. And if you don't use, I hope by the end of the talk you'll be more confident about using them. So they are used by millions and millions of users who generate lots of data. That brings us to big data. So what are the properties of big data? And this is something I hope you all are very, very familiar with. It's characterized by three properties: volume, velocity, and variety. But what are the challenges of big data? They include capturing the data, curating the data, storing the data, searching the data, sharing the data, analyzing the data, and visualizing the data. But more importantly, I think the challenge lies in extracting value out of the data, okay? And there lies a tremendous amount of untapped potential in big data, which I hope leads to big money if you write the right application and apply the right analytics to it. So there are many types of analytics, but to simplify, I'll just classify them in two buckets: basic and advanced. It's the simplest classification I could possibly think of. Basic analytics is all about what has happened in the past. And that has been the traditional focus of BI players. But when you combine basic analytics with big data, I think what you get is an ability to mine and report on huge amounts of data, which enables you to do long tail analysis, right? Which was something that was not possible before you had the ability to look into big data. But that is only great if you know what you're looking for. Now, the other category is advanced analytics, which really is all about what is happening right now, what will happen next, what is most likely to happen, what is most likely to happen if you give it a little nudge, okay? And predictive modeling is a subcategory of advanced analytics, which is all about predicting the outcome of unseen events. It is not about making a wild guess. It is not about shooting a dart in the dark. Predictive models are basically probabilistic models which are built on the basis of patterns seen in the data. And for the models to be accurate, the models to be reliable, the data needs to be error-free. Okay? That reminds me of a data quality joke. So this is a website which is basically allowing users to create a profile, and if the site collects users' personal information without any kind of validation, you can only imagine what kind of data you would be collecting in the back end. So this field, if unvalidated, is collected. Can you trust the data? I would say no. The answer that was revealed when analyzing the data collected on behalf of that field was that there are 6 sexes in the world. Male, female, yes, no, orc, and furry. Those of you who relate to Minecraft will appreciate the joke better. So in the era of big data, data is not static. And there are continuum challenges with regards to big data. It's flowing continuously. And dirty data leads to all kinds of problems. You make wrong decisions on the basis of the wrong data all the time, which leads to business problems. So how does semantic do and how does semantic deal with all this? So let me give some threat perspective and give an idea of how we apply big data analytics to our problem space. So in the current threat landscape, there are many ways to categorize the threats. But again, for the sake of simplicity, I'm going to categorize them in 3 categories. 1, threats which are targeting the consumer, which are all financially motivated. Okay? They're carried out by really skilled attackers and criminal enterprises. The second category is the attacks which are targeting corporations or enterprises. And these are basically after data theft, also known as exfiltration. So they're basically trying to steal your trade secrets, business secrets. And the third category is basically cyber war or cyber terrorism. And this is basically state-sponsored, targeting the country's infrastructure. So in all the 3 classifications of threat landscape, the attackers are really very motivated. They are very well funded, and they have ample resources and skills. So these are our opponents. Unfortunately, it's not a plain level field. They have no rules. They have to get it right just once. That means in terms of penetrating either the consumer or the enterprise or the infrastructure they're targeting. But we have to get it right all the time. We cannot afford to miss even a single attempt. So it's a never-ending chess game, and there is a constant evolution. We have to be extremely agile and nimble in order to meet this threat. So security is really a journey, not a destination. So let me give you a couple of examples of these attacks so that you relate to the threat landscape better. One example would be, say for example, you visit a particular website. The next thing you notice is that you've been given a warning that your computer is infected and your system needs to be checked for viruses. And of course, when you click OK, you're recommended to buy a software which will, of course, clean the threats on your machine. And now you would think that you're all cleaned up. But let me tell you, the malware never existed in your machine in the first place. So you ended up buying what we refer to as fake AV or fake antivirus. This has been a plaguing problem for the last 2 years, 3 years, I would say. A second example is you visit a site, and this is a little more interesting one. What you start seeing is some kind of messages about your file system not being accessible. You cannot anymore access your documents. And when you click repair, you get this kind of dialog box which looks all genuine and operating system-like, which is basically a malware. And it will gladly help you repair the files and get access to the files back. And it encrypts basically pretty much all kinds of data files that you might have, Excel, doc, PSTs, and so on and so forth. But of course, it gladly will accept the payment in order for you to decrypt the files, which it really isn't calling decrypting, it's calling repair the files and give access to your own data. So it basically hijacked your data, asked you to pay, and now you have to pay in order to get back your data. So you get your docs fixed after you have paid, the price was around $45 to $90. I think people would gladly pay $90 to access their data. So in all the above cases, it was all financially motivated. That was the consumer scenario. Now, in case of enterprises and targeted attacks, what we have seen in the last year is that there has been a 42% increase in targeted attacks in 2012. And here's the industry-wise breakdown of how the targeted attacks have been targeting various sectors, and manufacturing was leading the pack. And almost all targeted attacks are basically based on social engineering, paradigm, which in most cases starts off with a spear phishing email, which is a mail which is specifically tailor-made for the target enterprise or the user. And in terms of users who have been recipients of these kind of targeted attacks, this is the kind of representation of how the picture changed between 2011 and 2012. And in 2011, although the C-level executives were the most commonly targeted for targeted attacks, in 2012, the attention kind of shifted towards research and development. So these are basically tailor-made for the victim. So here's an example of a targeted attack email, which would, if it were to go out in your enterprise, I think reading the content of the email, I'm pretty sure 95% of the users will be very excited to click that email and open up the PDF. Who is not curious about salary scales? So if the user opens up the email and attachment, the PDF is basically going to exploit a vulnerability, and the malware gets run on a machine. In 2012, we saw such type of malware targeting close to 5,291 undisclosed vulnerabilities or new vulnerabilities. So once the malware is active on a machine, it spreads on all the other machines, basically looking out for confidential data. And the intent is to basically collect and exfiltrate all the data. So those were the couple of examples which give you a view of the threat landscape across consumer and enterprises. So how does the malware author really increase the chances of success? Well, they basically create a malware, and they mutate the malware till it bypasses the security product they would want to bypass. So they create one, and they mutate to get many, many variants, and that's how they kind of try to bypass the signature-based protection that the product might be using. Then they go about using web attack toolkits. Black Hole is a very common toolkit. It basically then exploits a target website and hosts the payload on the website. And then it is all about enticing the users to come to that website. URLs to that website are then spammed in emails. URLs are posted on Facebook walls. And once the user clicks on a particular link, unknowingly, he's really going to the website that the attacker wanted the user to go to. So they're basically targeting you. So how do we secure you? So once upon a time, antivirus signatures ruled. They were all about creating a fingerprint for a known malware and distributing it to the user base and remediating the threat. But with massive growth in new variants of malware and increasing sophistication, fingerprinting was no longer feasible or practical. That's where we kind of started applying machine learning to the big data and started building predictive models. These models are being built on huge amounts of data. Data that is continuous, collected from hundreds of millions of Norton or semantic users, and from lots of sources. The data may or may not be structured. It represents the fast-changing threat landscape. And to provide the best level of security, the models must be accurate, models must be robust, and they must be tolerant to concept drift. And by concept drift here, I imply the changing threat landscape, which dramatically varies in a very short period of time. So how do we do it? So we have huge repositories of data, basically files that we have been collecting over many, many years. We also crawl the web. We collect data from third-party feeds. We participate in vendor exchange programs. And then we have hundreds of millions of Norton users who all participate in a Norton Community Watch program, submitting anonymized data from across the globe, which gives us a global view into what's going on the end user's machines. So this provides us the most complete security data in the industry. Examples of data we collect are file fingerprints, information about files like, was it just created, or was it there on the machine for a long time? How did it basically spread from one machine to the other machine? And how did it come on the machine? Did it come through one of the browsers, or through mail, or through one of the more commonly exploited applications of the month? Where and when did we first see it across the entire user base? And then other file characteristics, like is it packed or is it obfuscated in some form which prevents us from analyzing the behavior of the sample? Does it communicate over the network? Does it crash? Does it hog resources? And how often does it run? And who runs it? So all this anonymized data about files, sites, and machines allows us to create a massive graph of all the objects of interest that we would like to offer protection to. And then we use all that data to basically build predictive models to predict the class of an unknown object that we are trying to analyze or come up to a conclusion about on the end user's machine. But the challenge is, what is an acceptable error rate? And what does an error rate really mean in this case? So what's an FP? So FP would imply here that I'm basically convicting a benign software and calling it malware, okay? So if I were to make that kind of mistake on an operating system component, it's going to be pretty catastrophic. I'm going to leave the machine unusable. And what is an FN? FN basically means that I'm letting a malware, I'm misclassifying a malware to think that it is clean and letting it run on the end user's machine, giving it a clean bill of health. So once the malware runs, it takes over your machine. There's user dissatisfaction, user distrust in a brand. Customer support calls go up, and there is tremendous loss of business. So both FPs and FNs are horrible types of errors for us to deal with. And I deal with this all the time. I mean, on a given day, I'll be optimizing for FPs, and we'll get complaints about there is a big FN. Then I'll be optimizing the models for FNs, next to realize that the FP rate has gone up and we need to pull back the models. Anyways, hence when we are building our predictive models, we are extremely conservative about acceptable error rates. Our view of errors is kind of a little different, okay? We care more about the population impact of the error. And by that, what I mean is, I can best explain by an example. So if I'm building a classifier which is basically trying to predict the class of a file, if the error happened to be on Adobe Reader, is it one FP or is it millions of FPs because Adobe Reader is on millions of machines? I would think it is the worst possible type of FP because it will pretty much impact every Norton user because Adobe Reader is so prevalent across all our user bases. So example usage of predictive modeling in our products. So I'll walk through how we apply predictive modeling. So we have definitely not seen every file in the world, and we have definitely not seen every URL in the world. So when a user searches for a topic, and the search engine is basically returning you the results, we have to basically go about classifying whether each of the search results are safe or not. And according to our analysis, close to 25% of the search results shown on the first page can be malicious, depending on the campaigns that are going on during that time. So the task really here for the predictive model is, should the user be allowed to click on that link or not, and how should we annotate that? So models are basically predicting whether the URL is safe or not. So let's assume that you ignored the warning and you clicked on the URL anyway. So the page now shows up and has some input fields. Page is a form. So the question is, should you really fill up the form and give up all your personal information in anticipation of some cash reward? So the model over here is basically trying to analyze the structure of the page and predicting whether the page is a genuine page, is it a scam, or is it a phishing? And by the way, the scam and phishing is an interesting distinction. They are very similar, but they are two different classes of problems that we have to deal with. Phishing is really targeting you and your relationship with your trusted brand, whereas scam is really targeting you. It's not targeting any brand, it's just tricking you in order to maybe take up a membership in lieu of personal information that you would give. let's imagine that the site has a program or application hosted on it. The question is, should the user be allowed to download the file and run and undergo the risk? Or maybe user didn't even have a choice, and the site silently slipped a piece of software on your end user's machine, which we refer to as a drive-by download exploit. So no matter how it came, the question is, should it be allowed to run on your machine or not? So here the challenge for the predictive model is that we have to predict whether the class of the file is good or bad. If the file just arrived, then we have all the context about how it came, from where it came. So we have a lot of context. The more the context, the better the prediction, because we can incorporate all that information. If the file already existed on the machine, then we have no context about how it came. So we are trying to predict to the best of our abilities with limited number of features. File is likely bad, file is likely suspicious. Let's say this was a case of an FN, we called it good, the file is clean. The program is allowed to run, and now when it starts communicating over the network, the question is, for the predictive model again, behaviorally to predict whether such a behavior being exhibited by this software, should it be allowed or should it be denied? If it creates more files, again, the predictive model is kind of trying to predict whether should I allow or should I deny. All these and many more scenarios involve predictive models. But the most challenging part is that what's a big deal about the fact that we have lots of data? What's a big deal about the fact that we have lots of real-time data or lots of streaming data? What is important over here is how much of that is labeled versus unlabeled. What percentage of the data should we really label, and what kind of sampling strategy should we apply on the data set in order to get a good sense of the data? And how do we even know what kind of sampling strategy corresponds to the data, because we don't know what the distribution of the data looks like if we haven't analyzed the whole data. We use label data to build classifiers, and then we deploy them, but do we know how it is really doing in the field? I mean, how do we really know that when it is calling something bad, that the file is indeed bad? So we kind of solve one problem and introduce another problem. It's making real-time decisions for the user on the end user's machine, and we have to monitor the error rates. And we have to make sure that it matches up to the TP rate, FP rate, and ROCs that we had come up with when we were trying to evaluate the classifier when we had trained it in-house. But how do we measure the error rate on unlabeled data? We need expert validation, so we need to pull in analysts and say, here's the model, here are the convictions it made, can you please confirm that it is indeed malicious or not, or it exonerated, and is it indeed clean or not? Security analysts are pretty expensive, and because they are the domain experts. But this is huge volume of data. Do we have that much of a manpower to deploy, to validate millions and millions of files that we are convicting or exonerating in the products? No. So we kind of leverage unsupervised or semi-supervised machine learning in order to solve that side of the problem. So we have supervised machine learning-based models deployed on the endpoints, on the back end, trying to make real-time decisions. And in order to complement and provide some kind of relief to the large volume of decisions that are being made by the endpoint, we kind of leverage unsupervised and semi-supervised machine learning approaches to offer some kind of sense of what the data is to the analysts. So we perform large-scale clustering on big data. So that kind of couples automation with domain experts. And so we are able to identify completely new patterns, identify completely new threat trends, and we are able to apply the analyst skills to the right set of problems. So instead of them having to waste their time and inspect each and every piece of file or each and every piece of URL or software, they can now do their analysis on bigger chunks of data, which is basically the clusters that we have given them on the basis of what we are seeing in terms of real-time data that is coming in. So that allows us to scale and speed to basically meet the speed of the threats that are evolving in the real world. So at the end of the day, good predictive models lead to better products lead to happy users, which leads to increased revenues. And in summary, big data has big potential. We are realizing it. Big data has lots of hidden values. But data quality is the most important aspect that you need to care about, even more with big data, because it is coming in at a fast pace, and if you don't take care of that, then it's going to impact you down the road somewhere. Deal with it before it becomes a big problem. Big data plus advanced analytics is really the next frontier for innovation, computation, and productivity. And in order to succeed, you really need to put these three pieces together: big data, data science, and most importantly, domain expertise. Thank you.
Hi, my name is Kathy Chang, and I'm a Senior Director of Business Development at Impetus. It's a software solutions and services company. If you could go back to the slide where you show manufacturing leading the chart.
Yeah. Oh, man. There are 300 slides, so bear with me.
Should remember the number and just... Thank you. The question I have is a little bit on the how you arrived at this chart, and I guess there's a source underneath. The question is, does this chart have some kind of relevance to how much value these industries see data solutions? So that would be, in your words, the data collection, curation, analyzing, storing, and visualization solutions. How important are those solutions to each of these companies in relation to their position on this chart?
So this data is basically collected via our consulting services, managed security services, which is really a consulting division, which goes and deploys products and solutions. So honestly, I wouldn't have any idea about how they care about or they relate to data solutions in their respective sectors, because that's really not the kind of visibility that we have. The kind of visibility that we have is what kind of threats these industries are exposed to and how frequently or how commonly they are being targeted. So this is really just a representation of the fact that of all the industries that get targeted for targeted attacks, this is the kind of classification on the basis of the incidents that we have seen specifically targeted towards those sectors.
Hi, I'm Chase Michael. I'm the CEO over here of Infinigraph. I'll be talking later today, so I'm going to make a big introduction. But what I'm really interested in is, it's obviously big in the news right now that China is doing something very aggressive and probably being supported by more than $1 billion. And I really would just like more of just more conversational about what's going on in your head. Obviously, you're at the top of the game here. This has huge implications. I mean, the amount of stolen secrets that could have been, and what's funny is we're not being told even probably a fifth of it, of what's really going on. So I'd love to get your, maybe, you're probably under disclosure of some sort right now. So if anything you can provide that would less news wash, that would be great.
That's why I had this slide which said, I reserve the right not to answer. But anyways, I think it's the challenge with targeted attacks and pretty much all the government sectors that we offer protection solutions to, their biggest concern is that they don't want the fact that they were exploited to be revealed. Okay, so I think that says it all, that even though we know how much of attacks are going on, the origin of the attack, the nature of the attack, and it is fairly easy to know from one attack incident to the other on the basis of common techniques, common components, and so on and so forth, that the attack was carried out by similar organization or organization with the similar engineering capabilities. And hence we can kind of always relate to the fact that who was the perpetrator behind the attack. Having said that, I still would not be able to answer your question for reasons of confidentiality.
So my question is like, the analytics happen after the fact that the files are authored and the website is present and the email is there, right? So why not actually target this at, while composing an email or while authoring a document or while hosting a website, right? So why not, it becomes easy if you have a signature available, and then after the fact it becomes easy to analyze it and then see whether it's a threat or not, right? Phishing or scam.
I think the problem that we have is, so the models are really deployed in real time. So there are two types of predictive models we deploy. We deploy on the endpoints. They're making real-time decisions for the user, whether a file is malicious, whether a site is malicious, whether the network traffic is malicious or not. And then there are predictive models deployed in the cloud, where because we are very performance conscious on the endpoint, we might defer some of the decisions to the cloud in order to help make the decision. Nonetheless, given the vast number of users, which is hundreds and millions of users, the amount of predictions that these models are making is tremendous. And so even though, and the other problem is, even if the analyst were to take a particular piece of sample and call it malicious, we do not benefit at all in terms of trying to signature it and push the signature to the endpoint, because it would then end up resulting in a definition bloat on the endpoint and your product would get bulky. And why do that when the model is already calling it malicious? There is no added benefit to the end user. In fact, models are more generic representation of what the threat is. Why push a fingerprint like a SHA-2 or MD5 or whatever to the endpoint? So we are better off just leaving things as is, which is let the model do what it's doing. It's doing right anyway. But the challenge is on the back end, we are never able to catch up if we were not to apply other kinds of modeling approaches to look at what the predictions are going on, right? So that's what I was saying. The supervised machine learning is creating predictive models which are being deployed in these scenarios. And then the verification of how these models are performing is being assisted via a combination of automation which involves unsupervised machine learning, which then assists the experts, because it is such a huge volume of data that it would otherwise not be possible. It would be millions and millions or billions of files, and an analyst in a typical day cannot process more than 10 samples, because he has to take the sample, he has to take it to the red network, run it, make sure it connects to the internet, see what kind of malicious activities it does, and then call it malicious. And in fact, calling something malicious is much simpler than calling something clean, because in order to call something clean, he has to prove the negative. That is, it does not do anything malicious, so all the code paths have to be exercised, everything has to be analyzed. Calling something malicious is very, very trivial. I run it, the moment it does anything malicious, I call it malicious, end of the day. So, yeah. Anybody go first.
Okay, so this is Puneet. I consult Visa for payment processing. So I have a question. Like, as a world leader security company, are there processes in place, for predictive analysis, using this big data analysis for malware attack for users based on their browsing patterns and provide them recommendations?
Yes, and that is something, so I would say it is one of the features that we use in our classifiers. So the browsing pattern, the kind of sites. So we also have a product, a technology which was probably the only technology very well known 5 or 6 years ago, called RuleSpace. And it used to do URL categorization, okay? So URL categorization and the kind of sites the user visits becomes a feature in one of our models, which is already deployed on the endpoint, right? So when you land on a website, it categorizes the website, uses the category as one of the features to predict whether the new website that you're going to, is it likely malicious or not. So if you're known to visit business sites, news sites, and so on and so forth, and then you're suddenly landing on a manufacturing page, that would take into account the risk that might be there, because, are you going there intentionally, or have you been tricked to go there? Or did the browser force you to go via some kind of redirects? So those kind of information are taken into account both to detect phishing as well as scams.
We thank you very much for an excellent talk. I like the way you presented. A lot of pictures, one word, few words on the screen. It was very easy for us to understand. We appreciate your a great speech.